Alright, it has been a long time since I have done videos on math. The CHistrue channel has gone back and forth, math, philosophy, math, philosophy. It's basically philosophy at this point, but I want to do a couple of videos on math. It's been a little while. I'm going to need your help. Honest critiques. I'm a little rusty, so bear with me, but give me your honest critiques as to how well this went. This one is on fun with dividing by primes. First thing I'm going to demonstrate is I'm going to demonstrate the fact that for primes other than 2 and 5, if you divide 1 by a prime other than 2 and 5, you will get a repeating series of decimals every, you get a repeating series of p minus 1 decimals on to infinity. So if I divide 1 by 7, I get 0.142857, 142857, 142857. That's 6 decimals repeated to infinity. 6 is 1 less than 7. If I divide by 3, I get 0.33333333 to infinity, but that could also be 0.33333333, and 2 is less than 3. 11 works. 1 divided by 11 is 0.0909090909. That's repeated every 2 to infinity. That's repeated every 2 times, but it's also repeated every 10 times, and 10 is 1 less than 11. It does not work for 2 or 5. Now, if you are not familiar with Fermat's little theorem, some background information on it can be had from my video, Fermat's little theorem concisely proven. I did it a long time ago, back when I was more in the A game in terms of mathematics and science-related subjects. I've been veering away from that. Actually, well, mathematics. I've been doing a lot of science, but not quite as much mathematics. So I think that I don't know if that was a unique proof or not. I doubt it was a unique proof, but watch it and let me know if it was. What is Fermat's little theorem? Fermat's little theorem is if I take some a to the power of p minus 1, p being a prime, and a is relatively prime to that p, okay? Then what I'm going to get is some multiple of that p plus 1. So in other words, a to the power of p minus 1 is modularly equivalent to 1 mod p for any a that is relatively prime to p. Now, why is that important to what we're about to do? Let's get into it. If I divide 1 by p, I'm going to get a series, and again, the p is relatively prime to 10, okay? So the p cannot be 2 or 5. I'm going to get a repeating set of digits repeated every p minus 1 times. How do I know that? Well, let's start off by noting the fact that 10 to the power of p minus 1 is equivalent to 1 mod p. Therefore, if I were to divide 10 to the power of p minus 1 by p, I would get some number with a remainder of 1. Okay, so that's a really, and of course that's p is relatively prime to 10. Notice when you divide 1 by p, you're going to go through a series of long division where you're going to make use of the fact you just keep adding zeros and zeros and zeros. And so it's as if you're dividing p by however many zeros you go out here. I guess in this particular case we can make it as if you're dividing p by 10 to the power of p minus 1. But then you're moving the decimal point back to being just after 1, so it's a rough equivalence. You're going to get the same string of digits, you're just going to get a different position for your decimal point. So if I divided p by 10 to the power of p minus 1, I get some string of digits as regular digits and not decimal digits with a remainder of 1. But in this case, I'm going to get a string of decimal digits going through a long division process with a remainder of 1 down here, where I'm dividing the p into 1 here, get a string of digits, but then I'm dividing the p into 1 here, and I get another string of the same digits, and then another string of the same digits and a repetition. Okay, so that's going to happen every p minus 1 times. Okay, so again, you've used Fermat's little theorem to show that that 1 divided by 7 is going to repeat itself every 6 times. Pretty neat. But the fun doesn't stop there. And again, your honest criticisms and critiques are welcome. I have occasionally flubbed a video and I've had to redo it, and I've had faithful viewers point that out to me. So including one time I did an improper integral. Okay, and I redid it and hopefully did a pretty good video, but you didn't hear that. So in this case, I'm going to explain why it is that if I have a series of ones, and this isn't a decimal series, it's just a regular series of ones, p minus 1 times, and divide by p, I get some number with a remainder of 0. So if I have 111,111, which is a series of 6 ones, divided by 7, I get a remainder of 0. That will not work for a p of 2, 3, and 5. 2 and 5, well, that's obvious. We're using base 10, and that creates a problem if we use base 10, just like we noted before. But also 3 doesn't seem to work, and I think that is curious, and I think it may have to do with the fact that 10 is 1 mod 3. So that doesn't seem to work. But in general, it will work. And note why it works, which is what we're going to discuss next. If I have this series of ones, that's going to be equivalent to 1 times 10 to the 0, plus 1 times 10 to the 1, plus 1 times 10 to the 2, all the way down, plus yada yada, 1 times 10 to the p minus 2. Okay, well, each one of those is going to be some mod p. And none of them are going to be exact multiples of p for obvious reasons, because our p is relatively prime to 10. P is not 2 or 5. And it's also not 3, which is again, another curiosity that I'm not fully able to account. Now, I'm going to submit to you that each of our remainders, if we were to divide each of these numbers by p, each of our remainders would be different. And the reason, again, is because our prime is going to be relatively, cannot be 2 or 5, and so it's going to be relatively prime to 10. So each of these is going to be a different mod p. One is not going to be A is not going to be B. They're going to be different whole numbers. Now, if I add all these up together, I get my string of p minus 1 ones, and that's going to be equivalent to 1 plus A plus B plus C all the way up to x mod p. Hope you can see that. But I also submitted to you that each of these are going to be different, and you're going to have p minus 1 different numbers added together mod p. But wait a minute, there are only p minus 1 possible mod p's. So what you're doing is you're adding each and every single number up to p minus 1 mod p. Because it only happens once, none of these ever repeat, and then you have p minus 1 times. That's going to be 1 plus 2 plus 3 plus 4 plus 5 all the way up to p minus 1 mod p. And that's equivalent to every single number up to p, adding, again, 1 plus 2 plus 3 plus 4 plus 5 all the way up to p minus 1, which according to Gauss's theorem is going to be equivalent to p minus 1 times p over 2 mod p. But wait a minute, that's a multiple of p. So that's just equivalent to mod p, no remainder. You're dividing evenly by p. All right, my friends, your honest critiques of the video, and I plan to do one more math video at least after this one, and I also want you to view Fermat's little theorem concisely proven, because I'd like to know if how well you like that proof. All right, thank you very much. CHistrue signing off.